because his coach, soccer coach, what's his name? Kevin said he wouldn't write it. He said, I don't want to write it. I would gladly write it, but I just don't want to write it. I'll sign it as long as you write it.
So he's just like, yeah, this looks good, I agree, and signed it?
So he's writing his own letter of recommendation.
It's not that hard, it's just
I
like
think
a
that's what he
page,
said.
right?
That's so.
Yeah, you don't want it to be more than a page. Yeah. And somebody
For
said for this for high school.
I don't know. I remember somebody
Carson,
saying
he's
putting
hands up.
I can see Kevin saying no.
Yeah,
She's
I'm
not my
pretty sure it was
girlfriend, and I don't know what I'm talking about.
All right, here we go. From yesterday. So relative extrema, we talked about relative extrema, peaks and valleys, occur only at critical numbers. There's two types of critical numbers. We have where the first derivative equals 0, which would be horizontal tangents. Those are smooth peaks and valleys, like rounded peaks and valleys. Or places where the derivative is undefined, which would be sharp peaks or sharp valleys. Okay? And not all critical numbers are going to yield extrema. Sometimes we get critical numbers that are other things like vertical tangents or points of inflection or things like that. And then we left off on some stuff like this. So let's just finish up a couple of these just to kind of practice. And then the goal for today is the skill we want to learn and practice today is finding all absolute extrema on an interval. Okay, and I'll show you, I have got some good stuff. This is one of the things, oh man, I tell you, this is good stuff. This is something I hear back from students in college all the time, and they say this stuff was extremely helpful. So this is coming up on some, like there's a tabular method that I've developed that I think works better than like what our textbook does in this situation. It matches the graphs. It's a good way to sketch curves because you can take the table and immediately apply it to a graph, and you'll see when we get there. But I'm particularly proud of this. I think it's pretty good stuff. So you're gonna like it. Okay, so on this one, are there any absolute extrema?
That's insane.
Are there? If
Come
so,
again.
where are they?
If there was some?
Absolute.
No,
Absolute
there's
extrema.
No.
There are none.
No.
You're right. There are none.
None.
Good. Okay. Identify the graph of f that has a local minimum value where f prime of a is equal to 0. And some of these are kind of hard to see, but like for example, that's not a smooth,
Yeah, I know it's not.
right? Does that make sense?
Is it E? B? Oh. That
So
one?
the answer is
B, right?
has a local minimum. Yes, it's B, exactly. Yeah.
Why?
I don't know.
Okay, and the reason why, here's why.
Seems the hardest.
Because look, we've got a horizontal tangent line right there, right? That's a smooth minimum.
Oh, yeah, yeah.
Make sense?
I did too.
Isn't that saying what this is telling us is smooth minimum?
Oh. Okay. I get it.
Okay, make sense?
Looking where it like touched the bottom.
Okay, how about this one? Identify the graph of a function that has a local minimum value at b where f prime of b is undefined.
Wait, where's D?
It's A.
It's A, yeah.
Yes.
How come? Because where the derivative's undefined, what's that telling us?
It's sharp turn curve.
It's a short extrema.
Yeah, sharp min, right? So sharp value.
Yes.
Okay. Okay, how about identify all the points on the closed interval from A to B at which local and absolute extreme values occur. So let's just pick these one at a time. So where are the local minimum points occur at what values?
Q.
Okay, so we get Q, everybody agree?
Mhm.
Okay, Q,
S.
S.
S,
That's it.
and that's it, right?
Yeah.
Local maximum points occur at
P, R, Does B count, or is that the end, so it doesn't?
Doesn't count.
Okay.
Okay.
Yep.
Absolute minimum values occur at,
S.
Q.
no,
Yeah,
absolute minimum points
A?
occur at
Well, it
A.
can't be A. Wait,
Exactly.
I thought
A.
the ends didn't count.
Okay, they don't count for relative extrema, right?
This is a point.
But they do count for absolute extreme, because remember what are the criteria for an absolute extremum? It just has to be the lowest or the highest point on some interval.
Okay.
Okay, so what we're going to find, and I'll repeat this again later, but what we're going to find today is that absolute extrema always occur. Really, there's only two kinds of places where absolute extrema could occur. What are they? Where would an absolute extremum occur? There's only two kinds of places where they could occur. And it's pretty open-ended, but I'm just,
Wait, ask it again?
yeah, what are the two types of places where absolute extrema could occur?
The tallest point.
The tallest point
shortest
or
point.
absolute.
Okay, well, so I got you. I mean, yeah, the highest or the lowest, but, okay, but like topologically, what types of places could those be?
Like, in real.
In the graph.
What?
Where
I'm
could
confused
absolute
by this
extrema
question.
occur?
Wait, isn't
Topologically.
it, it's a.
Morphologically.
Okay,
Oh,
so-
I need
Yeah,
a
only a
definition of
smooth.
it.
Well, no, it could be sharp.
Oh,
But it would be.
yeah.
I mean, if you think about
It
this,
has
they
to
have to
be-
occur either at peaks or valleys, right?
Yeah.
Or, so at
Endpoint.
relative extrema, we could say, that includes all peaks and valleys. Absolute extrema would occur either at relative extrema, or what are the other possibilities? Endpoints.
Oh.
Yeah, right? Like in this case, that endpoint happened to be lower than all the valleys, so the endpoint actually was the absolute minimum. You have to look closely, but what's the absolute maximum? Where does that occur?
P, sorry.
P, it looks like, yeah. So that occurs, this peak appears to be the highest place anywhere on the graph, okay? Oh, whoops, I guess we did,
He just higher than me.
yeah, so I
Yeah,
messed that
think
up. So the absolute minimum occurs at A. Where's the absolute maximum occur?
The blind.
At P, I guess. And then I don't know if those are supposed to be tied or not, but we'll just say it's at P. Okay, so here we go. Location of absolute extrema. Absolute extreme, if f is some continuous function on a closed bounded interval, then absolute extrema must occur at endpoints or at extrema, right? But where do we find relative extrema? We find relative extrema always at critical points. Didn't we say that all relative extrema, all relative extrema occur at critical numbers? Some of those critical numbers might be false alarms. So we got to come up with a strategy. Do we want to check all the critical points to see if they're relative extrema when we're looking for absolute extrema? No, it's too much work. All we'll do is we'll just find all of the critical numbers on our interval, and we'll just check them all and see which is the tallest and which is the lowest, right? That's it. We just need to find the highest and the lowest places on our interval. They can only occur at critical points, some of which may not correspond to extrema, but all extrema would have to occur at critical numbers, right? And then the endpoints, and we'll just see which one wins. Which one wins the maximum race and which one wins the minimum race. So our guidelines for finding absolute extrema on a closed interval would just be find all the critical numbers of the function between A and B, right? We're going to check the endpoints anyway. So all we need to know are all the critical numbers between the endpoints. We're going to evaluate the function at each critical number. We'll evaluate the function at the endpoints, and then the least of those values is the absolute minimum, and the greatest of those values is the absolute maximum. Does our strategy make sense? Right? find all the critical numbers and the endpoints, and just evaluate the function at all those places to see which is the biggest and which is the smallest. So let's look at an example. How about one like this? So here's f of x. Our interval, we have a closed interval from -1 to 0. Okay? So we need to find the critical numbers though, right? And I wanna also just look carefully at the terminology here. So critical points, that's really not the right word, but we really want to say there are critical numbers. The critical numbers are the values of x where the derivative is undefined or 0. Critical points would be if we made those ordered pairs, but we're not really doing that. The ordered pairs. Well, I guess in this sense it's used correctly. In this sense it's used correctly because we are looking for the y value. So they have to either be at critical points at the locations on the graph, which correspond to critical numbers, or the endpoints. But notice here, we say we're going to evaluate the function at the critical numbers. Find the critical numbers. Sometimes textbooks do a poor job, I've noticed, of interchanging those two things. Critical numbers are just input values only, not ordered pairs. Critical points are ordered pairs. Okay? So when we're doing a problem like this, we're just trying to find the values of x where the derivative is undefined or 0. So those are critical numbers. Okay, so that's first step. Find critical numbers. Oops. Critical numbers. Okay, so how do we do that? What do I need in order to find critical numbers? What do I have to find first?
Tangent.
Well, I mean, yeah, you're indirectly, but the derivative, right? Critical numbers depend on the derivative because where do critical numbers occur? Where the derivative is 0 or where the derivative is undefined. But in both cases, we're using the derivative, right? So we need the derivative function. Let's do that. Here's f of x. This is a really simple derivative. It's a polynomial. What's our derivative?
9x squared minus 6x minus 3.
Okay, so then we want to know where is f prime of x equal to 0. Is our derivative undefined anywhere? How would you know? Where would a derivative be undefined? The derivative is just a function. Where is the function undefined? .9% of the time, where do you think a function's going to be undefined? Like, I'll show you an example. You guys tell me, what if I have some
I'm gonna feel
function?
really stupid in a second.
What if I have some function g of x equals 2 plus 1 over x? Where is that function undefined? 0. How come?
Because 1 over x.
Because I end up with a 0 on the bottom, right?
Yeah.
Normally, the kinds of places where a function would be undefined would typically be places where you're dividing by 0. Could also be where maybe you're taking a square root of a negative number or something like that, right? But places where we get red flags in our function. Are there any red flags in this polynomial?
No.
Polynomials are literally the word we use is well behaved in math. They don't have any place where they're undefined. Their domain is always everywhere, all real numbers. So we're fine. There are no places where the derivative is undefined, and let's say that f prime is, here's how we'd say it in math. F prime is nowhere undefined. So we get none of those types of critical numbers, but it might have some zeros. So let's find out. Let's set our function equal to 0 and find out. 9x squared minus 6x minus 3 equals 0. Okay, let's solve that equation. What do I do?
Minus off for x. Right?
What should I do first though?
You factor.
Okay, factor out 3, okay.
Yeah.
And 3 is a constant factor?
Yeah.
So another thing I could do, which is equivalent to that, would be just dividing each side by 3. I can divide both sides of an equation by a constant. That's fair game. I just can't divide both sides by a variable, right? Because then I lose solutions. But if I divide each side by 3, what do I get on the left?
3x squared minus 2x minus
Minus 1.
1.
Minus 1. Okay. And so now we've got to, this is really good practice. You guys are going to get so good at solving equations because we're going to start doing a lot of that. What are our options for solving a quadratic equation? Factoring, quadratic equation, completing the square, right? Now, what about, quadratic formula is the ace in the hole. That always works. When would we probably complete the square? Because I think it's quicker and easier than quadratic formula in certain situations. But where would that be? Like, I would say this one's kind of disqualified. We wouldn't really want to do it here for one big reason. What's that? The 3. Yeah. If you have a leading coefficient other than 1, you probably don't want to complete the square. You could. But the other thing we could maybe do is factor this, right? Factoring also is way quicker and easier when it works, right? So how would we factor this one? Well, this would be one where we could factor by grouping, right? But the coefficients are so small that there aren't very many options here, right? So we can just kind of power through this one. We could say, okay, if this thing factors, we know that I'm going to end up with numbers here that multiply to -1 and numbers here that multiply to +3. There aren't very many different combinations of that, right? So we know the only factors of 3 that would be convenient for us are 3 and 1, right? So now, is there a way that we could stick a -1 and a 1 here in such a way that the cross term is going to work? That's the part we're trying to get to work, right? Well, there is. Where would I want to put the negative? Right, when I FOIL this out, I'm going to want to multiply. If the negative's going to, we have a -2, don't I need the -1 to be multiplied by the 3?
Yeah.
Right, and the +1 to be there. Does that make sense? If I'd done it the other way, I wouldn't get the right cross terms.
Yeah.
Right, everybody get that? And so then you just kind of, okay, that's the way it seems like it would work, then just FOIL it and see if it does work. Do the cross terms work? 3x squared minus 3x plus x gives me -2x and then -1. So yeah, we got it factored. You see my point there, how quick it is? Now, if this had been like a 12 and that had been a 24, I mean, then you don't want to mess with it because there's so many different factors that multiply to 12 and 24 that it's too much, right? That's where you would just fall back on quadratic formula or factoring by grouping or something, right? Magic numbers and grouping. But here's one where, yeah, there just are so few combinations. Just try them and see if they work, right? So what does this mean then? My zeros are. Okay, one of them is 1. X equals 1. What's the other one? Okay. So which of those critical numbers are we interested in? -1/3, yeah. 1's no good, how come?
It's not in our.
It's not in our domain, right? It's not in the interval in which we're evaluating this function or analyzing this function. So this guy we can just cross out. This is the one we keep. Okay, so now here is where we start to use these tables for the first time. These tables are so cool. Here's how the tables work. So with a table, you're going to make a row for x, and that just becomes the x-axis. Okay. Beneath that, for now, we're just going to make a row for f, and we could go ahead and make a row for f prime. Let's just include that. I don't know what just happened there, but okay? And then we're gonna go ahead and put our domain on the first row for x. We're going from -1 up to 0. Okay, those are our endpoints. And we had one interior critical number. That was at -1/3, which would be about, if we wanna, that's about like what, right there? If we kind of wanna put it in roughly the right spot. So those are, in the x row, those are the important x values. One critical number and two endpoints, right? Well, let's look down vertically. What's happening, what's the value of the derivative at that critical number? 0, okay? We don't even really need that row for now, but we'll just include it just so we start getting used to it. The row we're interested in is this row right there. Okay, because now what we're going to do is we're going to evaluate the function at each of those three places. So what is f of -1? I'm going to get what? -3,
12.
-3,
Oh, shoot.
+3. So I get 3. So 5? Is that right? Is that what you guys got?
I evaluated the derivative at 1. -1.
-3 -3. So it's minus. So -3. Oh no, actually -1. I think, right? I think we get -1.
-1, yeah.
Okay. So look, that acts like an ordered pair. There's an ordered pair. X is -1, Y is -1. How about at -1/3? Ooh, yikes. Well, what's that gonna be? So I'm gonna get -1/9 -1/3 +1. So -4/9, those are +5/9 +2, so 2 5/9, so something like 23/9. Is that what we get? No, sorry, not. What did I say, 9? Should be, that's wrong. No, that's right. I think that's right, isn't it?
Looks to be correct.
You guys can, yeah, I think that's right. Okay. And then at 0, it's easy. What do we get at 0?
2.
2. Okay. So then we get these three ordered pairs. What's our absolute minimum?
-1.
-1. Yeah. How come? Because that's the smallest value of y in that row, right? Okay. So this tells us absolute minimum. What's our absolute maximum?
23.
23/9. Yeah, that's right.
Oh, that's good.
See how that works? And what's this one? That's just some loser, right? That's a critical number. That's one of the numbers that just didn't pan out. It's the right endpoint, but it was neither the highest nor the lowest point on our interval.
So it's
Okay.
gonna be average. It's your average.
It makes sense? Give me 1 to 5 on that. See what we just did there? Okay, let's try another one. Let's practice that idea. Okay, how about this guy? Find the absolute extrema, if they exist, on this interval. Okay, so
Are we gonna have to use the quotient rule?
we are.
No.
Gonna have to use quotient rule. Yeah.
I was hoping it disappeared like it did.
Yeah, I was
No,
hoping
it
that was
doesn't.
a unit that we
It-
left in the past.
It doesn't know. That one is.
That
That one's
Yeah,
never
Yeah,
getting.
let's
It's never gone.
put it in the hospital and skip that.
So what do we got here? Quotient rule. Good practice.
Okay, so it's the bottom
Low to
first.
high.
So 3 plus x, and then
Minus
yeah,
one.
minus 1.
Good.
And it's
Minus
minus
4 minus
4
x
minus x.
times
plus
3. Oh wait, no.
Times 1, okay, good.
Times one.
Divided by,
Yeah.
3
You know what I meant.
plus x squared.
okay? So that's gonna give us, if we simplify, I'm gonna get a -3 minus 4 is -7, right?
Yeah.
I'm gonna get a minus
And
x
x
plus
cancel.
x, they cancel, good. Divided by
9x.
3 plus x quantity squared,
Yeah.
okay? So then, what do we know about our critical numbers here? Where is our derivative undefined?
-3.
Okay, is that important?
Yeah.
I think so.
Well, is it? No, it's not.
It's
It's
not
not
in
our
our
domain.
It's not in our domain, so it's
Uh,
superfluous. Okay.
that's
Okay,
what?
so then, superfluous.
Superfluous.
It's a good word, superfluous.
Superfluous?
Superfluous.
That sounds like a Mary Poppins word.
Does it?
Superfluous.
Superfluous.
All right, well, the Mary Poppins kind of guy. So then, do we have any interior critical numbers? Because is our derivative, is it
Uh-uh.
0 anywhere?
No.
No, because where would our fraction equal 0? Fractions equal 0 when the numerator is 0. Fractions are undefined where the denominator is 0. So our numerator is nowhere 0, so we don't have any zeros of our derivative, right? Okay, so then let's make our table.
Okey-dokey.
We really only need 2 lines on this.
Okay.
Our domain goes from 0 to 3 with no interior critical numbers. So what are the places where we check the value of the function?
0.
0 and 3. What's the value of the function at 0?
4/3.
Okay. And what's the value of the function at 3?
1/6.
So what's our absolute minimum?
1/6.
Right there. Our absolute minimum is going to occur at x equals 3. Our absolute maximum occurs at 0.
Yeah.
And doesn't it make sense that there could be no interior places where the function has an absolute minimum or maximum, because they would have to occur at relative extrema, right? They'd have to occur at places where the function turned, and it doesn't. The function, it might turn someplace, probably turns at -3, but that's outside of our domain. Okay? Let's try another one. Not one like that.
Hold up.
Ew.
I think that's a tomorrow problem.
No, last one for today. How's that?
Fine.
So this one isn't so bad. We can do this.
This is so bad. That's garbage. Do you see that?
So let's see.
So
So
we
we put we multiply 24
So we multiply
times
24 times 11
13.
divided by 13.
Good, good.
Hold up.
So we get 264.
What? Wait.
13ths, x to what power?
The -2.
How did you do that?
-2/3.
13.
Okay.
You're a wizard.
Plus. What?
Is it 13?
The heck, bro.
-2/13.
Say it again?
I guess
It doesn't
you're
have to be.
right.
Isn't it a 13?
Oh, 13, sorry.
No, you're good.
Plus,
Okay, we'll forgive
Is
you.
it 13?
plus what now?
Isn't it 264?
Yeah,
Over
264
and then it's
13ths, x to the,
11/13.
Yeah.
okay, good. So then what can we do with that derivative to make it simpler?
We
Uh-uh.
will put the x on the numerator.
Can we factor out a 264 over?
Sure we can. Let's factor out a 264 13ths, and let's go ahead and factor out the least common power of x.
What?
Okay.
How do you do that?
So then,
This is.
remember this stuff? We did this. This has been a while.
I
But if
don't-
we have like bases, we want to
remember
factor
anything.
out the least power of, which is negative 2/13, right? So we'll factor out a 2/64 x to the negative 2/13, and what's left behind from here?
One.
Yeah.
1, exactly. 1
One.
plus
X to the
To the
9. Wait,
to the
is it 9/13 or is that totally
X, just X.
to the x,
Just to the X?
right?
Because it'd be 13 over 13.
Because if we're going to
Oh,
divide
I
away
see.
x to the minus 2/13, what's going to go here is x to the 11/13 divided by x to the negative 2/13, which gives us x to the 11/13 minus negative 2/13, which is 13/13.
Gotcha.
Okay, but remember, we knew that was going to happen. We knew if we factor
Sure
out,
we
remember,
did.
if we get from a, well, actually, we didn't know that was going to happen. Did we? We did, because normally we're used to seeing this from a product rule or quotient rule. So I guess we didn't actually know that was going to happen, but it did happen.
You knew that.
But it did happen, yeah. Okay.
Oh, we did.
We all knew it.
Okay.
So then we can write this as one big fraction because that's our goal. If we can write these as one big fraction, then we can easily analyze it by finding zeros of the numerator and denominator. So this guy goes to the bottom, right? So we get a 264 times 1 plus x on the top. On the bottom, we get 13x to the 2/13. Okay, there's our derivative, right? So now, critical numbers. We know that f prime equals 0 when what?
When,
When does the numerator
Negative-
equal 0?
-1.
When x is negative 1. Right? F prime is undefined when
At X equals 0.
x equals 0, because that's going to be when the bottom equals 0, which is when x is 0. Good. Right? So now we got everything we need. We have our function up there. So we just have to make our table.
Did you come up with this table?
Yes.
You should write a textbook. Put it in there.
Thought about that.
You have or you haven't?
I have. I thought about that. So interior critical numbers at 0, right? We had 0 and we had -1.
We threw you a signing party.
Lita,
Shh,
for you
okay.
to autograph the cover.
Okay. So now we just need to figure out the value of the function in all those places. Well, what is f of 0? That's an easy one.
0.
0. Okay. So we get the point 0, 0. Whoops. Must be green. What's f of 1?
Oh gosh. That's really type it in, Carson.
Well, what's 1 to any power?
1.
1.
So
Okay.
24.
So,
So-
Plus
whoa.
11.
Right.
So,
So
35?
35.
Yep,
Okay.
oh shoot. I didn't love that.
How about at -1?
Chrissy's just
Negative
the opposite.
35.
Oh.
Okay, so what about this? So at -1, is -1 to the 11/13 going to be, there's only two possibilities, right? Yeah, what's it going to be?
I'm calling
Negative
it
one.
negative 1.
Wait.
Negative
One,
1.
positive 1.
It's negative.
It's
-1 because
Plus
it's
or-
not full
because
square.
it's not
Two
two
different
full
negative
square.
full
One.
square.
It's negative.
it's negative. That's what I've been saying.
It's
the whole
negative.
time.
How come?
Because
The
it's
11.
not 12.
Because of the numerator.
Oh.
Yeah.
That's what the power you
Okay.
take,
Because
right?
now think what this is. This is like saying
X to the 11.
this is a 13th root of -1. The 13th root of -1 is -1. To an odd power is -1.
Yeah.
Right? Make
'Cause
sense?
you can rewrite fraction
So
exponents.
does that mean that
as
the
a root
11
and an
one
exponent.
is
Yeah.
positive
Yeah.
one?
So okay, so what about this one? Yeah, this is gonna be +1. Exactly.
Oh.
Because we've got the 13th root of -1, which is -1, to an even power is +1, right?
Okay.
So then, wouldn't you agree that this is going to be an intermediate number? That's going to give us -24 plus 11 is -13. Okay. So we
Alrighty
get -13, and then at -2, who knows? Like we got to just plug that one in. That's going to be a weird one.
Go Carson, you have like 15 seconds to do this.
So
Actually,
I was
24
really close.
times the quantity -2 to the 11/13ths.
Okay.
Plus 11
Got it.
times the quantity -2 to the 24/13ths.
I refuse to
What's the second one multiplied by? What's the coefficient?
The coefficient is 11.
I have to see.
-82 points.
Yeah, that sounds about right. Yeah.
Yeah. That's what I was thinking.
So we got a winner, right? That's going to be our minimum, absolute minimum, and that's our absolute maximum.
We did it!
Right.
Yay for calculators.